Howdy everybody, welcome back to Lab Hours. Today we are going to be doing the first of 3 mini lectures on hypothesis testing. Alright, so this is hypothesis testing 1. We're going to be doing hypothesis testing single means. So we're trying to find one single mu, and we're going to hypothesis test around that, okay? The Tommy triple for today is a little bit strange, because the best way, in my opinion, to understand hypothesis testing and to get the intuition and to get the process and the math behind it is to set it up in like some kind of story problem premise. So what I'm going to present to you is actually just a very real, super true premise that is definitely occurring here in the real world. And then we're going to talk about how we set up a hypothesis test and how to interpret the results, or whether or not we reject the null hypothesis, which is something we'll talk about in just a second. So let's go ahead and jump right in. And I'm going to jump right in by introducing you to my company, my airline company. It's called Wait 8 Too Late Airlines, or Wetla Airlines, if you will. And the entire premise of this company that I founded is that, on average, our flights are going to be delayed 8 minutes or fewer, and that is the entire premise upon which I have founded my entire airline. So, basically, across all of our flights, we want our average flight delay to be no higher than 8 ever, at all, okay? So what we're going to do is we're going to, as a company, make sure that average wait times across every single flight that we've ever done stay below 8 minutes, you know? It can be delayed a little bit more than that sometimes, but we want it to average under 8 for a lot of really good reasons, okay? But one day, I'm the CEO, I started the company, but one day we hired this intern from some school like BYU or somewhere out west, I don't really remember. We hire a lot of interns, and one day this intern comes up to me and he says, "Hey boss," and I said, "Why are you speaking to me? I'm the CEO, but I will entertain it." "What, intern?" And this intern says to me, "Boss, I was crunching some numbers, and I'm not like 100% sure that our average wait time across the company is actually lower than 8 minutes. And I say, "Oh, intern, who do you think we are, intern? I founded this company with this premise that our average wait time across the entire company is 8 minutes or fewer," right? Let's just say it's 8 minutes right now. That's my entire point, intern, of this entire airline. And he goes, "Well, yeah, boss, but I've actually been crunching some numbers, as an intern, just out here crunching numbers. And, I took a sample of, just 100 of our flights, and I found that the average flight delay across those flights was actually 8.1 minutes. And I said, "Well, intern, that's all right and good, but like, what was the standard?" I was a stats guy. I did econ in my college days. Like, what was the standard deviation that you got from your sample? And he tells me, "Well, boss, I had a sample standard deviation of 0. Just 1/10 of a minute." All right, and I say, "Okay, well, that's plenty interesting. That's fine." In fact, he told me the number wrong, and I heard it wrong. He actually said that the standard deviation was a full minute. Okay, so let's go with that. Let's forget that I messed that up with this intern right here, right? Okay, so he's telling me this, and I'm like, "Okay, intern, that's pretty great, all right. But do you understand how many resources I've sunk into Wait 8 Too Late Airlines? Wetla is on the side of all of our airplanes. It's in all of our promotional material. And it's in like people are coming, if they have their Capital One rewards card, they can come to like the Wetla Lounge. You're really going to tell me that we have to like change the whole name of the airline, change all of those materials? That would be a crazy thing to do." And he goes, "Yeah, boss, but it's just like, we don't want to be like dishonest and like make this whole premise that our wait time is 8 minutes, and if it's actually higher than that." And I'm like, "Okay, I agree with you, but you're also an intern, okay? I am very acquainted with the real world. I say interns are frequently wrong, so I'm definitely going to need to be very convinced." So what I tell the intern is I say, "Okay, intern, if there is a less than 1% chance that you are wrong, that you've And by wrong, of course, what I mean to say, intern, is if there's a less than 1% chance of seeing what you saw in the data, if the true mean is actually 8 minutes. If there's a less than 1% chance of seeing what you saw, then I will accept that the true mean can no longer be 8 minutes, okay? I need it to be less than 1% because I need you to be very certain, because to change the whole name of our airlines, we'd have to change our listing on the New York Stock Exchange and all sorts of stuff like that, okay? So if there is a less than 1% chance of seeing what you saw in the data, if this assumption that we're making about our airline is actually true, then I will accept that this assumption that we're making is probably not true, and I will be willing to change and admit my mistake to you, okay? And we'll change all the names and we'll change everything like that. And I say, so intern, go ahead and show me that you are correct, that there is a less than 1% chance of seeing what you saw based on a reality where the true mean is 8 minutes, okay? This is the premise that I wanted to set up, okay? This is this idea of a hypothesis test that we're going to get into. I've swapped out of character now. Hopefully you can tell from my masterful acting. This alpha level right here, and this entire premise suggests that we have two competing hypotheses about the world. The first hypothesis is what we call the null hypothesis. That is the hypothesis that follows the status quo. That is the assumption that we're making about our airline. In this case, it's that mu is equal to 8, okay? Our hypothesis is that the average wait time across all the flights is 8 minutes. That is what we are operating under. That is kind of our operating assumption, right? Wait 8, too late. But what the intern in the story is presenting is an alternate hypothesis, an H1 as opposed to H0, if you will. And the hypothesis that the intern is presenting is not that the true mean is 8.1, because the intern knows that this is X bar is an estimator, and it comes with a certain region of like variance, right? Because estimators have variance, like we talked about last mini lecture. No, what he's actually proposing here is that the wait time is it's higher than 8 minutes. The true average wait time across all the flights in our company is higher than 8, and he's suggesting that because he took this sample and saw something higher than 8. So let's talk about this. This is the premise, okay? But the question is, which state of the world are we actually in? Which state of the world is it more likely that we're in? Which state of the world is it more comfortable for us to assume that we are in? To say it in a different way, okay? This is the premise. Let's check that off. And it only took me 8 minutes to do that. Would you look at that? How do we actually set up this hypothesis test? Well, what I'm going to do is I'm going to take all this information here, I'm going to copy it over to the next page, and let's set up a hypothesis test, okay? Okay. Here's my foolproof technique for setting up a hypothesis test, okay? I want you to follow this format. If you're not comfortable with your own formats, this will set you up for success every single time, okay? So, the first thing I want you to do is I want you to take your null hypothesis and your alternate hypothesis, put it right over here, put all the things that you know about the problem over here to the left, put null hypothesis and alternate hypothesis over here kind of in the middle, and draw a little dotted line. On the left, write test statistic, or just test stat. And on the right, write critical value, or just crit val is what I'm going to write here, critical value, okay? Here's what we need to do. Hopefully you recognize that X bar here is going to be distributed as a normal variable. And in this case, its mean was 8.1, and the sample variance that we got was something like 1 squared over 100. Okay, because that's what these numbers are. So, here's the question, okay? If we're living in a world where mu is actually 8, what kind of like, how likely are we to see this data? That's really what it comes down to. And then it also comes down to how comfortable are we with the chance of having of changing incorrect of changing when we don't actually need to change. Okay? In this case, the airline CEO is not very comfortable with that, as we're going to illustrate. Okay? So what I want you to start with is this critical value side. And you're going to remember from last mini lecture that the critical values are values on like, wow, that is certainly a bell curve. You're going to remember from last mini lecture that critical values are values on a standard normal or a t or a chi-squared distribution, okay? They are in units of standard errors usually, especially for means, which is what we're dealing with right now. So what we need to do is we need to set up a critical value that will reflect how comfortable we are with the chance of changing when we don't need to change, and that also reflects sort of the direction of what we think the world might actually look like alternatively. So seeing this, we have an alternate hypothesis that's greater than, okay? And we have an alpha of 0.01. So basically what we're saying that we should change what we do if there's a less than 1% chance of seeing something something that is extremely large, right? We would assume this number right here turns into something that is much bigger or much more extreme than we should expect it to, right? So the first question we might ask ourselves is, okay, based on our understanding of what we're testing for, which in this case is a mean. In fact, let's just put a little question mark there. We know that x bar and means are generally distributed normally, okay? Or as t's, which is fine. In this case, we're going to ignore the t distribution for 100, and I'm just going to use the z-score, even though we have an s, right? At the end of the day, they're super similar to each other, so the difference is not very big. Your regression softwares like Stata and stuff will always just give you a t-test anyway, but just for now, for teaching purposes, I'm just going to use the normal stuff, okay? Just the z-scores, okay? So just to get that out of the way as a disclaimer, on the standard normal table, what is the number, what is the critical value that has 1% of all the observations you would see if n were infinity? If n was infinity, what is the number on the z PDF, the standard normal probability density function, such that you would see a number that big or bigger only 1% of the time? Basically, what is this value right here such that you have 1% of the distribution to the right of it, and in fact, let me put it in red to keep our color scheme consistent, such that you have 1% of all the possible outcomes that you would see if n were infinity to the right of it, and 99% would be that big or smaller, okay? Why have I filled in this little area right here? Well, I've filled it in because if we're living in a world where we should change, we might expect to see statistics out here when we standardize this data, okay? That's what this test statistic is going to do, and we'll come back to that in just a second. But for the first thing that we need to do is we need to figure out what our range is where we would decide, okay, we should change, okay? Now, if we call this just the z-table, right, which, again, I have predicated on the fact that this should probably be a t distribution with 99 degrees of freedom, all your statistical packaging software will do that for you. In this case, I'm just going to make it easy, okay? But let's just call this the z-table. What is this value right here, this critical value? Well, let's go back to tmorg.org/downloads, right? Here it is. Just reload it so you can see it, and let's take a look at that distributions, estimators, and probability tables document, okay? Let's go look at the z-chart. And we remember that the z-chart gives us the values with probabilities to the left. And we happen to be looking to set this problem up for the z-value that has 99% of the distribution, or the area underneath the distribution, to the left of it. That should be pretty easy to find. Let's just come here into the middle of the chart, find something close to 0.99, and use that as that z critical value. And I'm looking, and the closest thing I can find to 0.99 is probably this 2.30123. 2.33. let's just stick with that one. Or we could use 2.32. I'll just go for 2.32. You know what? Why not? Let's pick this number as z equals 2.32. And now we're just going to leave it there for a second, okay? That is the number, the critical value on the z table, that has approximately 99% of the distribution to the left of it, okay? Area under the distribution, if you will. Now having done this, again, we took our greater than and we took our 0.01 from the alternative hypothesis and from the level of comfortability of our airline CEO, and we used it to pull this z is equal to 2.32. Now, what we're going to do is we're going to come over to this other side of our little test interface here that we've drawn, and we're going to take this information here that our intern observed from his sample, and we're going to standardize it into a z-score, or a test statistic, some number that will fall somewhere on this line. And if it falls over here to the right of 2.32, we're going to say, okay, we should live in an alternate hypothesis world. We should change. But if it falls anywhere to the left, because this is, a greater than type of question, if it's less extreme, or falls anywhere to the left in this case, because we're only looking at the greater than side, what we should do is we should not change. We should continue to live in our H0 world, or in our null hypothesis world. Basically, if we get a number that falls in here somewhere, we should reject the null hypothesis. We're not proving this one. We're just saying it's pretty unlikely that this one is true, right? So we should get rid of it. And we should go in favor of this one, right? To say, the average flight delay is greater than 8 is not super nice. It's not a super useful thing. Practically, it's like, okay, is it 8.1 minutes or is it 25 minutes, right? But you can say it's not 8. So, but, if we get a number that sits in here, we shouldn't change. We would fail to reject the null hypothesis. We should not change. We should just stick with the status quo. Whoa, no, no, no. Okay, so let's take the data that we saw here and standardize it, okay? What do I mean by standardize? Well, in this case, how did we get from x bar to z? We remember that x bar minus mu over square root of s squared over, n. This is actually technically distributed as t n minus 1, but this approaches a z standard normal distribution, right? So we're going to take this right here, the formula for our estimator, and we're going to just straight up plug in the numbers, and that will give us a test statistic. That will give us a z number. Okay, so let's do that. In this case, what is x bar? X bar is 8.1. And in this case, what should mu be? Well, it should be whatever mu is in the null hypothesis world. We are trying to test against the status quo world where we currently live, so use whatever is in the null hypothesis as the statistic that you're testing for. In terms of testing for means, which is all we're covering today, mu is always going to be in your null hypothesis. It's always going to be equal to something so that you can plug it into this test statistic. So let's do that. In fact, I'll put the test statistic in red. 8.1 minus 8 over the square root of s squared, which is 1. 1 squared is 1, over 100. Great stuff. Cool. So let's go from there. Let's solve this. And in fact, this one turns out to be really easy to solve. Hopefully, you can see that the square root of 1/100th is 1/10. And so we get 8.1 minus 8 is 0.1 over 1/10, which is actually just equal to 1. Okay? So our test statistic, x bar minus mu over, in fact, let's throw this, I'll just move it over. In this case, for this sample that our intern collected, x bar minus mu over sigma squared divided by n is equal to 1. Okay, great stuff. Now, that is how we set up the test. These are all the steps that we need to do. And one thing that we're going to find out is that this number is going to fall to the left of 2.32. But all of this right here is how I would set up, solve out, and run a test, okay? And we're going to talk about how to interpret it, what it means practically, different potential scenarios on the next one. But that is going to be the second part of the Tommy triple. That's how you set up the test. And now let's talk about to reject or not to reject. I'm just going to copy all of this back over, okay? And we'll mess around with it a little bit too. Oh, there we go. So let's paste this in, okay? You will notice, hopefully, that 1 is less than 2.32, which means if I were to plot 1 on this z table, it would end up here if we had 2.32 right here. What that means is that we cannot say that there is a 1% or smaller chance of seeing what we saw in the data if we live in a mu equals 8 world. In other words, if I'm the CEO and my intern shows me this, I'm going to say, intern, this data isn't like convincing enough to me that this is actually true, right? You haven't convinced me this is likely enough to be wrong for me to change my mind, okay? And so the intern will be all, sad. They'll probably get fired for wasting the CEO's time, right? But the main way to interpret this, right, is like, you can interpret it in terms of test statistics and critical values because they're in units of the same thing. They're both in units of standard errors of whatever you're looking at. But sometimes that's not always like super clear. So one other way that you can interpret this and figure out whether or not to reject or not reject the null hypothesis is to find a probability value associated with your test statistic and your critical value. So let's do that really quick. We already know the probability value of being as extreme or more extreme than 2.32 on the z table, right? That probability, or the probability that z is greater than 2.32, we already know is equal to 0.01 approximately, okay? But what is the probability that z is greater than 1? Let's go back to the table really quick. With a z-score of 1.00, we get a probability of 0.8413 to the left, okay? So over here, I'll put it right here, up at the top. This is 0.84-ish. So that means the probability of being more extreme in a greater than world would actually be something like 0.16 or something close to that, right? What does this tell us? What does this actually tell us? It's equal to 0.16. Well, basically what it's telling us is in a null hypothesis is true world, in a world where mu is equal to 8, we have a 16% chance of seeing an x bar that is this much higher than 8 or higher, okay? So basically, the intern has shown us one potential outcome of a sample of 100 flights. And this potential outcome is, 8.1 minutes. But we say, in a world where mu is equal to 8, right? In the world we think we live in, there's a 16% chance of seeing that, even if mu is still equal to 8, okay? But the airline CEO is only willing to change the way that he sees the world if there's a 1% or smaller chance of seeing an x bar this big, based on sample size and, standard deviation. So in this case, the bigger p-value and the less extreme test statistic both tell us the same thing, okay? They tell us we should not reject the null hypothesis. And it's not quite that the null hypothesis is true, it's just that we can't reject it at this level. But there's a lot of moving parts here. Let's say, for example, that our, let's say our airline CEO is a little bit more loosey-goosey. He's a little bit less conservative. Let's say he were okay with, you know, a 5% chance of seeing something this extreme even in an H-null world, right? Well, we know how to test against that as well, right? We know that the z-score that would give us, and let me throw this in green really quick to not get too crazy. We know the z-score that would fill that criteria, right? If this is 0.05 to the right, and this is 0.95 to the left, we know that that z-score is 1.96, and you can get that from the table. I just happen to know it because it's a very common one. It's actually not 1.96. Sorry, let me back up on that one. That actual z-score is 1.64. Okay, ish. And so the question becomes, like, even if I'm a little bit more willing to change when I don't need to, if I'm still in an H-null world, should I still change, right? And the answer in this case is no. In fact, what is like the lowest alpha, or the biggest alpha, for which I would be willing to change, right? In this case, or not willing to change, but what is the biggest alpha, my biggest willingness to change, such that I should change given what I've seen? In this case, it would actually be an alpha equal to 0.16. If I said to the intern, hey, I'm willing to change everything about the airline if there is a 16% or smaller chance that what you're seeing is actually a result you could see, if we're living in the world I think we live in, I will be willing to change my mind, and I will change my mind, okay? That's how we interpret this. The one other thing I will point out to you, potentially, is what if the intern hadn't said the wait time is greater than 8? What if instead, let's change a couple things. Let's say the intern saw, he observed 1,000 flights with the same, the same outcome. What would that look like? This would be the square root of 1 over 1,000, and that new test statistic would actually look different, right? Because what is 0.1 over the square root of 1/1000th? That's actually 31, which is 0.1. That's 3.16, okay? Get out of here, calculator. What are you doing over here, bud? That would change the test statistic to, a 3.16. And now, all of a sudden, we'd be living in a world where we actually should change our minds, right? If we got this 3.16 because we saw the same X bar and the same level of variance across more observations, now I'm living in a world where, like, okay, you've convinced me. This is actually consistent, and it really looks like we are actually living in a world where our average flight delay time is greater than 8 minutes, right? That would be a big problem for me, okay? One other potential thing that could happen, let's say instead of 1,000 flights, the intern observed 250 flights, okay? And then let's also say, for example, this would be the square root of 1 over 250, and we'll calculate that in just a second. But then let's also say the intern didn't just come up to me and say, hey, our wait time is greater than 8 minutes. What if the intern said to me, hey, I don't know what our wait time is, but I don't think it's exactly 8 minutes. Like maybe the CEO said, the average flight delay time is exactly 8 minutes across our entire company, and I will stake my life on it. And the intern comes up to him and says, I don't think it's 8 minutes based on what I've seen. It looks closer to 8.1 or 8.2, okay? What would this actually look like? Same alpha level, but now I'm just going to change the alternate hypothesis, okay? Well, the first thing I should do before even touching my test statistic is I need to redraw this graph, okay? That's the first thing I want to do. First thing I want you to do is pick good critical values. So let's redraw this graph. All right, oh, wow. You'd think I'd get like really good at drawing bell curves because I do it so much, but no. Fun fact. put 0 at the center. Now, instead of looking for a number that has 1% of the distribution to its right, now I need to look for a number, I need to look for two numbers. And I need to look for two numbers such that the region that lines up with my alternative hypothesis in total adds up to 1% of the area under the curve, or alpha percent of the area under the curve, right? So I don't know exactly what those numbers are, but the probabilities that I want look like this. Okay, I want 0.99 in the middle, I want 0.005 to the right, and I want 0.005 to the left of this, this region right here. Okay, hopefully you can see how hypothesis, from this drawing, how confidence intervals might relate to hypothesis tests and how they're sort of the same thing, but we'll touch more on that later as well. Let's go ahead and calculate what are these actual values. And the really nice thing is because z is symmetric, I can just find the z-score, the negative z-score that has 0.005 to the left of it, and then I'll just put the positive version of that number on the right. And as I go through and I look, the number that pops out to me as being the most, like just the closest, would be in between negative 2.57 and negative 2.58. So let's go with negative 2.58, just for funsies, okay? So if I put negative 2.58 and I put positive 2.58 here on the standard normal table, the standard normal PDF, these probabilities hold. Okay, this is true. So now my question is no longer is my test statistic like greater than or less than? My question is my test statistic more or less extreme than these two critical values that I've found? So now that I have these critical values here on my graph, let's come back and let's finish actually calculating the test statistic. Okay, let's pull the calculator back up again, if it be willing, you know. 8.1 minus 8 over the square root of 1 over 250. Calculate. That gives us a score of 1.58 approximately. 1.58. Now, if I were to take this number right here and plot it on this graph, it would fit about right there. So the question becomes, should I change my mind about the world that I'm living in? Should I change my assumption that the mean is actually 8? The answer is no, because that test statistic that I found is not more extreme than these numbers that I've just picked up. Or to put it in other words, the chance of seeing what I saw in the sample is not sufficiently small for me to change my mind. Okay? If I wanted to find this p-value, I would take this to the table, I would find this probability right here, and then I would also take the symmetric version of it, right? Just like the probability value, the two-sided or two-tailed probability of a 2.58 is, you know, it's 0.01 because it's that plus that. In the same way, if I want to find the p-value for this test statistic, this 1.58, I would take this probability right here, but I would also take its symmetric version, or I could just double it because the z-table is symmetric. You just can't do that for every distribution, only for the symmetric ones, right? So hopefully you can see how, like, changing the alternate hypothesis, changing your alpha value, changing the number of observations that you look at would change, you know, your conclusion that you should draw. And in fact, again, let me show you, what if the intern, instead of looking at just 250 flights, looked at 400 flights? Would that actually change anything? It's a good question. Let's look at this. Square root of 1 over 400. Let's recalculate this with 1 over 400 for the test statistic. Okay? And we get a test statistic of 2. All right? That's crazy that it's actually just straight up 2. And for this alpha equals 0.01, I still shouldn't change my mind. I'm still not comfortable changing my mind. But what if alpha were, you know, what if alpha were, for example, 0.05? Well, then we've established at this point that these negative 2.58 would actually be negative 1.96 and 1.96. So in that case, would I be living in a world where I should change my mind? And the answer is yes. The probability of seeing a test stat of 2 would be more extreme, or would be smaller, than seeing a test stat of 1.96 or negative 1.96. So I would reject the null hypothesis, and I would change my mind in that case. Okay? That's pretty much everything. And we're going to practice this over the next 2 mini lectures, so if these concepts still aren't sitting perfectly well with you right now, do not worry. We are going to do it over and over again. But this is the cool part of this class, right? This is the real-world application. This is the meat and potatoes. We are finally here. We are doing the cool thing, and it's a great time. Today's lecture, we set up a real-world premise for some time you might actually want to run a hypothesis test of a single mean. I showed you how to set up the test, how to pick critical values, how to calculate a test statistic, how they're kind of the same thing, and then we talked about how we interpret the results of those comparisons of test statistics and critical values, what it means to reject the null hypothesis, what it means to fail to reject the null hypothesis, and how changing certain parameters of the test can make things more or less certain, right? So that's going to be it for this mini lecture. Next time, we're going to be doing hypothesis testing 2, which is going to talk about testing proportions, which in themselves are just averages, but they're in fractions. And we're going to talk about hypothesis testing differences of means. So today we tested whether the mean was greater than or not equal to 8. But next time, we're going to test whether the difference in 2 averages is different from 0 or different from 5 or different, something like that. So we'll get into that. And of course, if you have any questions, if you're in the class, email tmorg.ta@gmail.com. And if you're not in the class, email labhours@tmorg.org, or just leave a comment, like the video, share the video, subscribe. You know what to do. So thanks for stopping by. Hopefully we'll see you next time, and we will continue the meat and potatoes of the class in the next mini lecture. Hope to see you there. Thanks for coming, and have a wonderful day. Bye-bye.